Okay. Now we are going to talk about the overlapping generations model again. So this is going to be the OLG. And we're going to continue where we left off. But now we're going to add within generation a heterogeneity. And in particular, it's going to be heterogeneity of endowment patterns. And what this is going to do for us is we're essentially going to have borrowers and lenders within a generation. So there's going to be motives, interest for some people to borrow and some people for lend from people who live within the same generation. And we'll talk about non-monetary equilibria, where there's only within generation borrowing lending. And then we'll talk about monetary equilibria, where they'll both be within generation borrowing and lending, but in addition there'll be another asset that is traded across generations, and that will be money. Okay, and this is going to provide a setting for us to talk about some classic issues that involve inside and outside money. Where inside money is money that is essentially evidences of private indebtedness, and outside money is going to be some evidences of government indebtedness. So that's where we're going. Okay, so here's going to be our setting. There's going to be time is going to go 1, 2, 3, forever, and there's going to be 2-period lived people, just to recall that, and they were born at times t equals 0, 1, 2, and so on. So these are going to be the initial old. These are the initial old people, and the way we're going to do this is we're going to say there are j. We're now going to say there's j groups of people for each t. We're going to keep for each t, and there's nj people in group j. That's the way we're going to do this. Okay, so agents in group j, people in group j, they're endowed W1j when young, and they're endowed W2j when they're old. So the 1 here means 1 is first period of life, and 2 means the second period of life. Okay, and we're going to assume that as before, we're going to assume people have preferences. um, um, that are going to look like, well, they're going to have preferences. We'll say, actually, we'll say everybody's alike, so I won't index them by J. If you're born in period T, you have preferences over and over consumption today and consumption tomorrow. And I'm going to make these log preferences. Why log? Because I can compute savings functions very easily. Okay. So if I assume that for all j, and notice this, I'm imposing a kind of stationarity in that I'm not indexing these by stationarity, because I'm assuming the same endowment patterns repeat generation after generation. So what this structure is going to imply is there's going to be a saving function that we can get as we did before. We computed the saving function in our last lecture. The saving function, which I'm going to write for person of type J, it's going to be RT is going to be the rate of return between time t and t plus 1. For this J person, it's going to be half of the person's first period endowment minus the second period endowment divided by RT. So this is how much you save. And what this tells you is if W1 is big relative to W2, the person will tend to be a saver. If W2 is big, a saver or a lender, you could say a lender. If W2 is big relative to W1, then the person will be a borrower, the first period of life. And we're also going to say at time t equals 1, there are old people, they're initial old people, and in total, I'm not going to tell you much detail, in the aggregate, they hold H units of inconvertible currency. And H is named after Milton Friedman, who used to use the term high-powered money to distinguish it from other types of money. And soon we're going to be encountering why he made that distinction, because this is a model that'll actually let us talk about this in a really convenient way. Okay, so let's do an example. This is kind of a simple example of a saving function. Let's assume that W1 of a type, I'm going to assume two types of people. There's going to be the type 1 person, and they're going to be endowed like this. They're going to be well endowed when they're young, but not endowed at all when they're old, where alpha is greater than 0. And the type 2 person, my notation, I've said this person is going to be endowed like kind of the opposite, and beta is greater than 0. So which you can kind of guess, this person is going to be a lender, and this person is going to be a borrower. Okay, and how do I know that? Well, I'll calculate the saving functions. If I take f of r1, the first type of person, I get this person saves half of his endowment, regardless of the interest rate. Second type of person, if I calculate this person borrows this amount, this saves this amount, denominated in time t consumption goods when they're young. So that's how this goes. Okay, now we're set up to go. So we have saving functions for our agents, and we're going to talk about two types of equilibria. First, we'll talk about a non-monetary equilibrium. Okay, the way this is going to go is, so we have to define what a non-monetary equilibrium is going to be. It's going to be a sequence RT. T is going to go from 1 to infinity of interest rates, gross one-period interest rates, and savings rates which I could call STJ for t equals 1 through infinity, j equals 1 through j, saving rates for everybody, such that this is going to be simple. This is what you do. This is what you do in undergraduate economics, because this is a version of Irving Fisher's theory of interest, his famous theory of interest from the beginning of the 20th century, such that the saving rates are on the saving functions for each person. So that's where the savings. So savings are optimal for everybody. And the second thing is, it's going to be a market clearing condition. If I take j equals 1 through j, all types, I said there were nj of that type of person. I take their saving rates, and this is going to be 0. So there's no net saving, 0 net saving. Or another way to say it is, this asset has 0 net supply, 0 net aggregate supply. So this says borrowing equals lending within a generation, within each generation, t greater than or equal to 1. It's just going to repeat. And this says saving choice is optimal. And I'm going to draw a picture of what this looks like. It's quite easy. This is a diagram, famous diagram. On this axis, I'm going to put, I'll put aggregate saving. Which is equal to summation nj f of rt over the different types. That's what this is. It's a function of r. On this axis, I'll put rt. So I'll put here. And this saving function I'm going to draw, well, it's going to be upwards, and here's 0. It's going to be upward sloping. And then here's the equilibrium saving rate. There's the equilibrium saving rate. If I had, and that's the end, if I had specified this economy so that the endowments varied across generations, then this aggregate saving function, which is written here, this is our saving function. That's our so this is savings. If I move this thing here, this is our aggregate saving function. It's RT. That's my aggregate savings, so I can erase it down here. That's the way this looks. Okay, and the way we've set this up with our little economy with alpha, let's say I have, say, n1 equals n2, j equals 2, that would be my example. I would have I would have my what I have to have is, if I add up the saving, if I do that example, I would have alpha over 2 minus beta over 2r sub t has to be equal to 0. That's the way this condition 2 would look. And then I can easily solve for RT as a function of alpha and beta. I'll let you do that. And I just want to, so this is our non-monetary equilibrium. Within each generation, people are just trading with each other, and there's no trade across generations. And I'm going to now put on a significant number. This interest rate R, that equilibrium, here's the value 1. One possibility is R, it looks like this, that R is less than 1. So kind of let's see what that might mean in our example. If we have alpha equal beta over R, that would imply that R is equal to beta over alpha, if I did that right. So this might be, this interest rate might be, it'll be greater or less than 1 depending on the endowments of the borrowers versus the lenders. That's just an example. So R could be greater than or less than 1. And that's going to open up the door to our next topic, which we're going to talk about now, monetary equilibrium. And this is going to be more fun. So it's going to be exactly the same economy that we talked about. And what's going to happen is we're going to seek an equilibrium in which the old people in the aggregate sell H units of currency, unbacked currency, which they're endowed with initially, the initial old, to the young for time t goods. Okay, so what we're going to seek, we're going to define a monetary equilibrium. It's going to be some sequences now. And what's it going to be? It's going to be, I'll just let a sequence be, if I put a vector above it, it means it's an entire sequence from t equals 1 through infinity. A sequence of prices, price levels, and a sequence of saving rates. And so a monetary equilibrium is going to be this sequence, and by this I mean x bar, x, just using this notation, that's what this means. It's this entire sequence for any variable x. Okay, a monetary equilibrium is going to, what's it going to consist of? It's going to consist of a triple of sequences such that, it's kind of what you'd expect, P is a positive sequence. It's positive for all t. RT, the rate of return on the 1 period gross interest rate on loans, it's a real interest rate, goods at, it's goods at t plus 1 per unit goods at t, is equal to the rate of return, the 1 period rate of return on currency. So this is the rate of return on, you could say, inside money or loans, private loans. Inside money is just private loans. It's an old language. Inside money, or some very famous monetary economists in the 20th century, or private loans. And this is the rate of return on H, which is our outside money. Okay? And so this says that all forms of money bear the same rate of return. So that makes the holder of them, the saver, is indifferent whether it holds in terms of inside money or outside money. And then the third condition is that the saving rates are optimal. So they're given by one of our saving functions. So, and one other condition is this condition, which says that, and if we think about this, this is going to be beautiful. This is the net saving of the young generation, which in a non-monetary equilibrium is 0, but now it's equal to the dissaving of the old. And this is their H divided by PT. So this is the net saving, aggregate, net meaning aggregate, of the young, and this is the dissaving of the old. And this is going to hold for every t greater than or equal to 1. So that's what we mean by a monetary equilibrium. So very good. So so now let's compute an example, kind of using our graph. We're going to go back to our we'll do this both with an equation for a graph. So I'm going to guess that there exists an equilibrium in which RT is equal to 1 for all t greater than or equal to 1. So this is going to be a stationary equilibrium. So we've seen enough to know that there's liable to also to be non-stationary equilibria, and that will surely be true. But I'm going to make this guess. And then, so what am I going to have to solve? So the equilibrium condition is just going to become a version of this. I just have to import this down here. So I write this down, summation j equals 1 through j, nj, and f of 1, that's my RT, is equal to h, and now this is just going to be a p. So pt is equal to p for all t. So that's what stationarity does. So stationarity gives me RT is equal to a fixed number, and pt equals p. I substitute that guess, and now I have to solve this equation. If I can solve this equation for a positive p, remember my p has to be positive, that's one of my requirements. Right there, then I'm in business. So let's go back and see what this looks like. So here's my saving, my aggregate saving, and here's my rate of return. And now I'm just going to draw my graph again. I'm going to draw it just like I drew it before. So this is my summation. This is my function, njf of r. Keep r in there, j. That's my aggregate saving function. It's upward sloping, given the way I've made my preferences. Here's 0. And what this is instructing me to do, what this equation is telling me to do, I stare at that equation, it's saying put 1 here, and then come down here and read h over p from there. And this works if, and only if, we'll put this here, our non-monetary equilibrium was less than 1. Was less than 1. So if the curve looks like this, I'm in business. So a monetary equilibrium may or may not exist. And the condition for a monetary equilibrium to exist, I call that R sub n for non-monetary. The condition for a non-monetary equilibrium to exist is that the stationary monetary equilibrium interest rate, gross interest rate, is strictly less than 1. Because this makes room for a monetary equilibrium to exist. There's something else interesting, which I'll say in passing, is this was the condition that if we use things we've seen before, monetary equilibrium exists, and this is what Samuelson's, one of his great findings was, a monetary equilibrium exists if and only if the non-monetary equilibrium is not Pareto optimal. So this is telling you, remember we talked a little bit about the welfare theorems and how Samuelson had created an environment in which the welfare theorems did not hold under certain conditions. Under some other conditions they did. And it had to do with how high the interest rate was in the non-monetary equilibrium. Well, that same condition is showing that arrives here, and this is indicating that when a monetary equilibrium exists, this valued fiat money is actually doing something socially good. It's improving things in this Pareto sense. So let's do an example. If we do an example, our little example with two types of people, with savers who are endowed alpha 0 and borrowers who are endowed 0 beta. And before we calculated, these are fun to play with because they're very easy to get your hands on the saving function. We don't have to do lots of dynamic programming to do the saving function. That's one reason overlapping generations models are interesting for solving, getting some insights really fast. So here's our savings function that we had before. I'll do that. That's our saving function. And I'm going to use this to write the equilibrium condition like this. I'm going to write this in a way that 20th century monetary economists would like, because it gives them an insight. They did like. Write the equilibrium condition as, just by rearranging, plus equals. This is the equilibrium condition for the monetary equilibrium. Okay. That's my condition, and I'm going to stare at it for a little bit. Just going to stare at it. So the left side is, this is the demand for savings. This is the demand for saving or lending, otherwise known as lending. So the left side has, this is lending. The right hand side is going to be borrowing. And there's going to be, so these are borrowings, or you could say issuers of debt, one period debt. And these guys, this is private debt. And this is currency that we could think of as having been issued by the government. And Samuelson said, yeah. So this we would call inside money, meaning it's issued by private borrowers. And this we'd say outside money, issued by the government to the initial old at time 0. And it's valued. So This is a framework that establishes conditions under which both inside money and outside money would be valued. And it's also a framework in which and governments in countries, especially various places, Latin America and other countries, and the United States, at various times, have taken a version of this equation, and they've noticed that inside money, they would say, competes with government money. An example, and what that means is, if you did a little comparative dynamics experiment here, is you would notice as you raise beta, I'll put this in here, as you raise N2 times beta, meaning that's a comparison across economies. So you raise this, meaning you raise the supply of inside money or private IOUs. The value H over P of government money goes down, or the price level goes up across economies. And that has motivated governments at various times to do things to limit private credit as a way to hold down the price level. Okay, so this is our overlapping generations model with heterogeneous consumers, and this was our graph. So thank you.